A very warm welcome to all of you joining online to this evening, if you're in the UK or wherever you are around the world, event on the current practices and future of structural use of bamboo. My name is Faith Wainwright. I'm a past president of the Institution of Structural Engineers and delighted to be chairing tonight. I'd like to just read the copyright slide. Copyright is terribly important, and to the institution's best knowledge, copyright permission has been provided for all the material that this broadcast is using, and it's therefore presented in good faith. If the copyright holder believes permission has not been forthcoming, then the relevant item will be removed, or by agreement, an appropriate acknowledgement provided to accompany the recording. Also, if I didn't mention it, you also have a button for useful resources, and I would encourage you to make use of that. So I come to our wonderful speakers this evening. Sebastian Kaminski is an associate at Arup and is a specialist in the structural use of bamboo. He runs iStructy in-country training courses on bamboo internationally. He has published a number of papers and guidance notes on using bamboo appropriately and was co-author of the latest ISO Bamboo Design Code, published in 2021. David Trujillo is Assistant Professor, University of Warwick, and Head of Bio-Based Materials at Atelier 1. David has authored or co-authored over 50 publications on the structural use of bamboo and has been deeply involved in the development of bamboo codes and standards internationally, including ISO standards. Amongst his publications, it is worth highlighting the new iStructy Bamboo Design Manual he co-authored with Sebastian. So I'm delighted now to hand over to our first speaker, Sebastian Kaminski.
Very happy to be here today to present along with David on bamboo, state of the art and future practices. And so David and I have actually been working together for over 15 years now. So we're very happy to do this presentation together, and we've collaborated on various different projects. So firstly, we have a poll, and if you're happy to, please could you complete it? The question is, which statement most closely reflects your expectations for today's lecture? If you're on full screen mode, please exit that and you can view the poll, and I'll give you 15 seconds or so to quickly fill that in before we move on. Great, thank you. So that's just very useful for us to understand the audience for today. So moving on, what do we think of when someone mentions using bamboo for construction? We probably think of something, maybe affordable housing, maybe scaffolding, maybe an informal bridge, but generally we'll think of something that's quite low cost, quite temporary. But actually, what can we do with bamboo? Well, bamboo in the round, we can do quite a lot. And there's been a lot of experience over the past, especially I'd say 25 years, 25, 30 years, there's been a bit of a boom in using bamboo in the round, which is in its unprocessed form, for a variety of different buildings. This is just an example of the sort of building that you can build with large diameter bamboo. We've got pavilions, which are 2-3 stories high. We have pedestrian bridges, community centers, luxury housing, and also affordable housing, which I'll talk about in a bit. So there's quite a lot of potential for bamboo in the round in construction. So I'm going to give a quick introduction to using bamboo. If you are more interested in finding about bamboo and state of the art and how to design with bamboo, David and I do an Institution of Structural Engineers course, which we run every year, and so you're welcome to sign up to that. So bamboo itself is actually a giant grass, it's not a tree. And this is a bamboo forest in Colombia. This is roughly where bamboo grows natively. So most of South America, Central America, and the southern part of North America, a large portion of Africa, and South and Southeast Asia or extending all the way to Australia. So it grows natively in a large portion of the world. And bamboo doesn't change diameter over its life. When it leaves the ground, that's its final diameter, and it goes through cell division in between the nodes. So on the left-hand side, you can see David pointing at a culm just leaving the ground, and it grows very, very fast. Within about 4 to 6 weeks, that's what you can see on the right-hand side. It grows incredibly fast. Within about 6 months, it's full height, and and then it starts to create branches, and it's mature after around 3 years, and after around 5 years, it starts to degrade. So the window to harvest is between 3 to 5 years, and you can compare that with timber, where timber typically needs at least 40, 50, 60 years before it's able to be harvested. So bamboo grows incredibly fast. So from that point of view, it's a very sustainable material. And a single stalk of bamboo is called a culm, and when they grow together, that's called a clump. So you might hear us referring to those two terms. And there's lots of different types of bamboo. They range in terms of different diameter, anything from 10 millimeters all the way up to 200 millimeters. Some species are actually are actually solid, but the majority are hollow. And on the right-hand side, you can see bamboo there. Now, bamboo's actually got these nodal diaphragms, which you can see in the image as this line across the culm, and that's a solid portion of fiber. And in between that, it's typically hollow. And so you've got the nodal diaphragm and you have the internode, which is the space in between those nodal diaphragms. And as I mentioned, there's over 1,600 different species of bamboo and counting. We're still discovering new species every year, and they range in terms of color, in terms of shape. Some are straighter than others. Some have nodes a lot closer. But there's typically only about, say, 10, 15 species that we use structurally for construction because they're large diameter. They tend to be straighter, so they're a little bit easier to use. So a brief summary of bamboo properties. The dry density is around 650 to 700 kilograms per meter cubed on average. Culm heights can vary from anywhere from 3 meters up to 30 or sometimes 50 meters. That nodal spacing between the nodal diaphragms is anywhere from 200 mil to 500 mil. The diameter can be as small as 10 mil up to 200. And as a general rule, the wall thickness for the solid species of bamboo is 10% of the external diameter. Why do we consider bamboo very sustainable and low carbon? Because firstly, as I mentioned, it grows very fast to maturity, and that makes it particularly useful if we're trying to fight climate change now. Then, if we plant something today, we can harvest it in a very short time period. Unfortunately, compared with the timber forest, if we plant a timber forest now, it'll take a lot longer to harvest. In addition, because bamboo is a grass, when you harvest it, it doesn't kill the plant. Unlike a tree, when you harvest a single tree, the plant itself dies. Bamboo doesn't. The plant itself survives underground and it keeps producing new culms. And therefore, the soil cover isn't completely reduced and you don't get that erosion. And bamboo stores significant quantities of carbon in the culm itself, but also in the plant underneath the ground. And it requires minimum energy to process when used in the round. So there are a lot of advantages of bamboo from that perspective. This table is taken from the Future Institution of Structural Engineers Guide, Manual for the Design of Bamboo Structures, which David will talk about a little bit more. But this shows characteristic strength and stiffness as recommended for the scheme design of bamboo. And this gives you a flavor of the sort of properties that we can use. And we're comparing it here to C24 and D50. So from a density perspective, it's closer to actually a D50, D40 or D50 hardwood. In terms of strength also, it's very good. Compression and tension and inflection, as you can see, you're more like a D30, D40 pushing a D50. In shear, it's a little bit weaker, but it's not that bad. One of the issues is the modulus of elasticity, and that varies very much on the species. So some species are less stiff than, say, a C24 softwood, but some are more like a hardwood. But as you can see, it's a very, very good material. We're talking about something much closer in general to a hardwood than a softwood. And how does it behave in fire? So like timber, it doesn't behave well. It typically chars. Now, timber has the benefit because when you do get charring, this portion in the center stays generally protected from the charred layer until the whole thing burns. Bamboo, on the other hand, because it has quite thin walls, a little bit of charring means you've lost most of the section. And you can see that on the left-hand side, that's rice cooked inside bamboo. It's cooked probably only for a few minutes, but probably most of that wall is completely gone, unfortunately. So you really have to protect bamboo from fire by protecting it with gypsum plasterboard or gypsum plaster or cement-based plaster. And we've done tests and we've shown that actually a cement-based or gypsum-based plasterboard can give quite quickly a 30-minute fire rating at least. But unfortunately, you can't use bamboo completely exposed to fire without any protection. Behavior in earthquakes. So people often say bamboo is flexible and therefore behaves well in earthquakes. And that's a bit of a misconception. Bamboo itself, if you try and bend it, it will snap. And so bamboo itself is generally quite brittle in most failure modes. If you take a piece of steel on the other hand, and you bend it, it tends to, most types of steel will tend to be quite ductile. And you can bend it backwards and forwards several times. The steel heats up, and you've converted the dynamic energy into basically heat, but you've got a lot of ductility. And bamboo buildings, so bamboo by itself as a material is generally quite brittle. Now, bamboo buildings can behave well in earthquakes, especially traditional ones. Firstly, primarily because they're quite light in general. And obviously in an earthquake, the force that you need to resist in an earthquake is directly proportional to the mass of a building. So lighter building means less mass. And in addition, we have those connections which can absorb some energy if they're well designed. And traditional buildings are generally quite well tied together. Now, modern buildings, again, this idea of flexibility of bamboo is a bit of a misconception. We really need to have good steel connections to be able to absorb energy exactly as you would approach timber in seismic design. So timber itself, generally most failure modes are also brittle, but it's those steel connections that can absorb energy. So exactly like timber when you're looking at bamboo for seismic design. And on the top again, you can see where bamboo typically grows, and on the bottom, you can see the areas of the world which are most highly seismic, generally speaking. And you can see many of those areas coincide: the west coast of South America, much of Central America, and much of South and East and Southeast Asia. So this means that there is good potential for using bamboo appropriately in highly seismic areas. But you need to keep bamboo in good condition. When bamboo isn't in good condition, the structure will not behave well in earthquakes, and we've seen this a lot after many recent earthquakes. These are just two photos I took after the Ecuador 2016 earthquake. This structure nearly fell down. Luckily it didn't, but most of the damage was actually due to rot, and that made it a lot weaker in the earthquake. In wind, bamboo is quite a light material. And in general, it forms light structures, and that means for winds it's a bit harder to design for, but it is possible. And Base Bahay have done a great job in the Philippines making typhoon-resistant housing that's made of bamboo. The structure is predominantly bamboo, and they just have good connections, and they've tied the structure down to the foundation. So in the same way as you design any other building for typhoons, it is possible to make a modern bamboo building typhoon resistant. In terms of durability, unlike some species of timber, bamboo does not have any naturally occurring chemicals which will help protect against natural attack mechanisms. So unfortunately, it's very vulnerable to beetles, termites, and rot. So for that reason, we have to protect it. And how do we do that? Firstly, we treat bamboo typically with boron, and that protects against beetles and termites very well. Unfortunately, you can't use boron treated bamboo outside because the boron just gets washed away. So we need to also keep it dry. So how do we do that? Simple durability by design. You have a good waterproof roof, waterproof walls, you elevate the structure, damp-proof membrane. If you've done that and you've treated the bamboo, the structure should last 50 years plus very easily. So we know how to make durable bamboo buildings right now. And this is a summary of standards around the world that use bamboo. The first one was in 2000, but the first detailed standard that contained a lot of design methods was in 2010, and that was published in Colombia. And the most recent one in 2021, which David and I worked on, is ISO 22156, and this remains the state of the art, and this contains the most recent design guidance and includes all everything that you need basically to do good structural design of bamboo in the round right now. So if you want to design with bamboo today, these are the three standards we recommend using: 22156 for structural design, 22157 for determination of physical and mechanical properties, and 15624 for grading. There's still a lot of work that needs to be done in this space, but this is a good start. So at least one can do quite challenging structures now following these codes. Now, where in a structure is whole-culm bamboo most appropriate? So we know that bamboo itself is quite strong, but unfortunately the connections are the weak point, and that's often where you get crushing or splitting. So because of that, it's best to use bamboo for elements in compression, where the connections are simplest, and also because we know bamboo isn't that stiff, it's best to use it in bending with low dead and live loads, and where deflection is less important. That makes it most appropriate for structures such as roofs, purlins and rafters, parts of structural systems in compression only, such as columns, and parts of structural systems in bending where deflection is less important, such as secondary beams and floor joists. And at the same time, of course, as I mentioned before, bamboo should be fully protected from water, sun, and rain, and therefore should only be used internally or externally when well protected by adequate roof overhangs. And this is one of my favorite images. This is in Colombia. This is a toll booth. And what you can see here is the designer has used bamboo in a very clever way. They've mixed it with different materials intentionally. They've used concrete for the foundation that touches the ground and that's most exposed to driving rain. They've used bamboo predominantly in compression. They've also used steel cables for the areas in tension. So intelligently use three different materials where they are strongest. Now, in terms of systems, there's one specific system which we think has a lot of potential. This is called the composite bamboo shear wall system. And this uses a timber or bamboo frame clad in a matrix of bamboo and plastered in cement mortar with a chicken mesh reinforcement. And that system has been proven to be quite earthquake resistant and wind resistant. And it's also fully code compliant, and it can have a design life of 50 years. It's based on the vernacular wattle and daub system from Latin America called Bahadeque, but improved using local engineering. And these are some examples from around the world, and anything from single story to two-story terraced housing in various different countries. And over 10,000 modern composite bamboo shear wall houses have been built since 1980. Most of them have been in Colombia, Costa Rica, India, Nepal, and Philippines, and Ecuador, but there's also smaller numbers in El Salvador, Mexico, Haiti, and other countries. But this system has a lot of potential, and if you are working in the affordable housing space, we'd encourage you to certainly look at this. And we've published a number of design guides on this in English and Spanish and French, and also it's incorporated into ISO 22156. Just before I pass on to David, I just wanted to finish off on what is the current level of knowledge on structural design of whole-culm bamboo. So we can design with whole-culm bamboo right now. It's still relatively in its infancy compared with timber. So for example, mechanical properties of various species. Some species are quite well studied, in particularly moso and asper and guadua, whereas other species are much less studied. In general, there isn't an enormous variation between species. There's more variation in terms of stiffness, in terms of strength. It's not as significant, but still we need more work in that space. But there is still enough to do good design. You just might need to do some testing for various rarer species. In terms of element design, there are good design equations for flexure, shear, and compression, and these already exist. Joint design is another weak area. We provided some methods in ISO 22156, but more testing is required. And unfortunately, often if you're doing an unusual joint design, it's not like Eurocode that you can pick up the Eurocode framework and just do a design from first principles following that code. With bamboo, you normally have to do some full-scale testing to validate it, unless it's quite a simple joint design. In terms of durability, we know how to make durable bamboo buildings now that can last 50 years plus. In terms of fire, we know that bamboo doesn't behave well in fire, so we have to protect it. And in terms of seismic design of systems, so this hasn't been studied that much. We know that the composite bamboo shear wall system has quite a lot of ductility. That's been studied the most, but very little testing, full-scale testing has been conducted on, say, moment frames or braced frames, We think they have some ductility, but it's probably limited. So that's another area which would benefit from more work. And now I'd like to pass over to David, who will talk about bamboo future prospects.
I'm going to talk a bit about the prospects of what we could do with bamboo. So firstly, let's talk a bit about the barriers to adoption of bamboo in its round shape and poles, culms. First, there's a barrier is acceptance. There's a perception of low status in some communities. It's sometimes called poor man's timber. Legislation, it's not recognized in the national building codes throughout the world. There are concerns about performance, which are maybe real or perceived. And of course, there's the issue of the fear of the unknown. There are some real inherent limitations. Sebastian's already mentioned the poor fire resistance, mainly caused because it's just hollow. It's got limited durability because it's hollow, and it has no naturally occurring chemicals. An interesting one is if bamboo is generally cheap because it's fast growing and simple processing, but if you're going to transport it very far, transportation costs start racking up because precisely the hollow shape. It's not a very efficient shape to carry around. It's also very susceptible to cracking, and that's due to its anisotropy and hollow shape. It has irregular shapes and sizes. It's natural, circular, tapered, segmented, which makes it difficult to connect. And many of these processes are quite labor intensive. Supply chains are complex because in some parts of the world, you don't find established suppliers that can provide you with reliable quality bamboo. There are lack of incentives, currently no real requirement for low carbon construction. So why would you go through all the difficulties that we've mentioned when you can continue using carbon intensive materials? And training, there are few trained workers, including professionals. And there's consensus, we're still lacking consensus about what constitutes quality construction. There are very many approaches to design and building. Some of these are not appropriate. So how can we address some of these barriers? So the first one is working through ISO standards, which is what Sebastian and I have been working on. Also working on national building codes, work that I've been doing in other countries. How can we address the fear of the unknown? At least, as Sebastian has mentioned, through the iStruct manual, we help create familiarity and we allow professionals to find a reliable source to answer their questions. How can we address fire? Sebastian's mentioned it, encapsulation, but there could be also other design considerations. Limited durability, as Sebastian mentioned, preservation and protection by design. Susceptibility to cracking is strongly addressed if you work with seasoned bamboo, but also some design considerations. And in terms of training, we have few trained workers, including professionals, but hopefully the iStruct manual is a way to move in that direction. And also in terms of consensus of what constitutes good practice, hopefully the work we're doing around ISO helps in that way. In terms of ISO, we have 3 published standards for bamboo culms, and we have 3 published standards for engineered bamboo products, which I'm going to be telling you a bit about. So, and they're more on stream for engineered bamboo coming along. So there is work. We are actually due to undertake revisions to these 3 standards. These 2 soon, and this one next year will be due to be revised. Talking of the iStruct manual, it is linked to ISO 22156, which is for design of bamboo culms. And so I'm just going to mention some things about it. It's got lots of guidance and solved examples. So hopefully it'll be a very useful resource. Which will be coming along hopefully by the end of 2025, and it will be free to download. If you're interested, at the end of my presentation, there'll be a slide with a link for you to register your interest. So I've mentioned the word engineered bamboo. So there are two main engineered bamboo products at the moment. One of them is laminated bamboo, which is a bit like glulam, but it's made of little pieces of bamboo glued together, and then these can form a board, and you glue these boards together. And the process is you start with the columns, you split them, you plane them, you either bleach or caramelize them. This is how it's made in China. In other parts of the world, the process is slightly different. Glued and pressed, and then this is your product. The second engineered bamboo product, main engineered bamboo product, is scrimber. This is what it looks like. And you start off with some strips, which are they're covered with a resin, and then they're subjected to compression force and heat, potentially, and cured, and then you have the final product. So one of the things that changes between engineered bamboo and bamboo culms is that now you have, because you have a larger section, you can now be having a section that could have very reliable and significant fire resistance. So research shows that laminated bamboo performs slightly worse than softwood, and scrimber performs slightly better than hardwood. So overall, you can say it behaves in a similar way to timber in a fire, and you can adopt its design procedures. And so that's a game changer with respect to bamboo culms. They also a significant change in reaction to fire. Here I've got some values from a manufacturer, and I'm comparing them against timber products. So laminated bamboo has a slightly, marginally better performance in fire than most timber products, just in terms of this criteria, S, and which is smoke production. And the scrimber products, some of them can have a fire performance which is comparable with cement bonded particle board. So it's interesting. They can have quite good fire performance. In terms of connections, it looks very much like timber, so you would have thought that it can be connected like timber, which is true to an extent. There are some failure modes which are slightly different, but fundamentally you can what's been demonstrated is that you can design it in a similar way to engineered timber. You can make connections that look like those in timber, so we don't have the issues that you have with bamboo that in the round, which the connections are peculiar. And so far, most of the research has been focused on bolts and not yet in screws or nails. But then you can make things that look like if they're made of timber. So here's some photographs from a manufacturer in China, and you can see, you start to see this is very similar to what you can make with timber. In terms of the durability aspect, because scrimber has quite good durability, better than laminated bamboo, you can start using it in applications that you couldn't do with bamboo in the round or natural bamboo, which is you can use it in cladding products. So there are products around the world that can be used with thermally modified bamboo scrimber. So it's an interesting also possibility. In terms of mechanical properties, because these tension, compression, and bending to an extent rely on the fibers, we have pretty good properties. Here I've got a video of testing bamboo in tension, laminated bamboo. You can see it's remarkably strong. Here are some values from a paper from 10 years ago that compared laminated bamboo versus scrimber versus bamboo in its natural condition and some timbers. And in general, you can see that the bamboo products surpass the strength of the timber products. But the one thing that we know that is very important in the design of with timber, which tends to govern design, particularly of beams, is deflections, which means it's governed by modulus of elasticity. And these products do not have particularly remarkable modulus of elasticity. If anything, it looks very much like a softwood. So for the moment, though you have remarkable strength, you don't have particularly remarkable modulus of elasticity. We believe that if you use tropical species of bamboo, this could be changed. So to tropical species like this, and you can maybe get 50 to 70% stiffer sections. If this is demonstrated in industrially made products, then this could be a game changer, because then you were talking about a product that is 50 to 70% stiffer than softwood. Yes, it is more expensive, but it is also more capable. So we believe that that's a really interesting aspect to look out for. One of the problems for bamboo is developing the scale of production. So I mentioned a moment ago is cost is a barrier for engineered bamboo. So this is a idea I've had. I'm not going to say it's necessarily the path, but it does reflect what manufacturers have done. The reality is that engineered bamboo as a structural product is relatively expensive, but it could be in part because of economies of scale. So one of the things that we can do with bamboo is help build that economy of scale by specifying bamboo, engineered bamboo products. But let's not start at the hardest part, which is engineered bamboo as a structural product. Let's start with the easy bit. So we start with non-structural applications like flooring, architraves, skirting, doors, etc., which have less stringent requirements for performance. And then we gradually move towards semi-structural applications, decking, mullions, non-load-bearing partitions. We move then to secondary structural elements like rafters, floor joists, wall studs, and so forth. Then we go to, for example, structures of easier building regulation compliance like roof structures and external structures. And then we finally start looking at pilot applications. So I think this is a journey that we can all be involved in. I know that only somewhere around here does it become sort of relevant to structural engineers, but it is a path, and it's a worthwhile path because, well, I'll elaborate that in a bit more in a moment. Why it's worthwhile, Sebastian's already covered a bit about its remarkable sustainability. Another thing that can help a path to help create the economies of scale that are needed are possibly develop products that sit somewhere between the bamboo culms and the full engineered product. This is because the factories for engineered bamboo are expensive to set up. And so you need large capital investment. And so you have a chicken and egg situation where it's, well, how am I going to make this capital investment if I don't know if you're going to buy my product? So one of the things we've been exploring is alternative. One that I've been particularly interested in is something I've called dowel laminated bamboo. That's the term I prefer, but it's frequently known as pimbu, which consists of strips of bamboo that are doweled together. And you can make quite a uniform product. It's remarkably stiff and strong. Here I've got a video, not a video, a couple of photographs of a demonstration that we did of a 40 mil reinforced concrete slab versus a 40 mil pimbu slab, if you like. And you can see it's not just strong, but also stiffer with the same load. We did this in an activity in an event place called Bamboo U in Bali. And it was just trying to drive the message clearly of how it works. In a project that we did earlier this year with the FCDO, we explored the possibility of building sort of straw-baled frames, wall panels, inspired by a system used here in the UK, but now entirely out of bamboo and straw with no timber. And so the system would use this product to make the frame, and then we infill it with straw. So it could be one way to use it. Now, where to source engineered and semi-engineered bamboo products. So most engineered bamboo products at the moment are made in China. There are factories elsewhere in the world, but by far the largest production is in China. There is a nascent industry of, well, business, shall I say, at the moment, more than an industry, of trying to plant bamboo throughout Europe, because there's demand for bamboo in Europe, and the idea is to bring it closer to Europe. And so there are some plantations coming along. Possibly one of the most advanced so far are in Portugal, but there are other places throughout Europe. But one of the things that I think is worthwhile noting is that sustainability goes beyond carbon and transport, because people always say to me, oh, but if we're going to ship engineered bamboo or semi-engineered bamboo products from far away, we'll have all this carbon, embodied carbon from the transport, which is true. But most of this would be shipping miles, which would be smaller than, say, in the land miles. But the other side to this story is the huge societal impact and potential environmental benefits of trying to grow a bamboo industry in the global south, which would foster a great deal of employment and opportunities there, and which in turn help foster the growth of their own engineered bamboo industries, which need the capital investment we were talking about. So I think we need to consider, when we talk about engineered bamboo products in the future, that there is a story that's more complex than just the embodied carbon transportation. We also have a story to tell about the societal benefits of this industry. Okay, so that's all my part to say. Here is a QR code if you're interested in the iStruct design manual, so that we have a database for those of you who would like to get hold of the manual once it's published. And thank you very much.
The recording will be available in the next few weeks on the iStruct website. And please do look at the upcoming events that are on the screen for further things that you might want to sign up for, and the highlighted resources. Just moving away from the topic of tonight, can I bring to your attention the Benevolent Fund, which is a really super thing to support. It provides financial and practical support to members and their families in times of need. So it could be a real lifeline. And if you would like to support this work, please scan the code here to make a donation. You will have to first log on as a member to access the donation page. Any donations would be hugely appreciated. So this brings us to the end of our session tonight. I keep saying tonight, but you may be joining first thing in the morning or in the middle of the day. Wherever you are, I would like to just say a final thank you and a huge thanks to the team at the iStruct for Olga and Gigi, and really appreciate their work. And I hope for all of you that have tuned in, it's gone smoothly technically. So our meeting is now closed. Thank you.